Welcome viewers to the seventh lecture of the course on non-traditional abrasive machining methods, and we have gone well into the discussion of horn design in ultrasonic machining. So, we will quickly finish that and take up some numerical problems and finish this part. So, what we were discussing was we were having this particular expression, that is from the final solution of the velocity due to the vibration, we have its expression as this one, and displacement will also have a similar expression. So, this means what is this displacement, as we had discussed that we were talking about? It is a displacement due to vibration. Okay, it is going to and fro. This is the vibrational displacement and velocity that we are talking about. So, at x equal to 0, we had discussed that the velocity is 0, since it is at x equal to 0, suppose we consider that velocity is equal to 0. You might say, oh, why isn't that the section in which you are connecting the transducer? So, how can the transducer end of the horn have 0 velocity? To this, my answer is we are taking the general case now. Let me draw a figure to discuss this point. This is the typical sine wave, and if I take the distance between 2 points which are completely non-moving, it is this pair of points. If I take 2 points which are always, which are having the maximum movement, it is this pair of points. What is the displacement? What is the distance between them? The distance between them is basically half the wavelength. Half the wavelength. What's the full length of the wave? The full length of the wave is this one. So, if I am asked to find out this particular length, I can also do one thing. The basic wave equation that I am dealing with, I can put conditions of 0 displacement or 0 velocities at these 2 points, solve for it and say that this length, as it is equal to this one, I can well solve for these 2 conditions and apply it as the length between these two. Okay, I will solve for this length between these 2 points, and I will say that it is equal to this one. Okay, that is what we are going to do. And how does it apply in our case? Our case is this. In our case, say at this point it is undergoing motion. Okay, it is undergoing vibrational motion here at this point, connected to the transducer. Therefore, from here there is a point at which there is no motion at all. So, if we draw the graph of motion versus displacement, it can be like this, same as this one. Okay, same as this one. Let me draw a clearer figure. If I say that, okay, I am drawing the motion against distance, so these are the corresponding displacements suffered at these points. So, basically it is vibrating in this manner, and this is the middle point at which it's a node point, there is no motion. So, if it is vibrating this way, okay, so I can find out this length to be half the wavelength, okay, half the wavelength, and I can solve it for this one also. I will say I will solve it for these 2 points. No motion points, node points. I will solve it for this, and I'll say it's equal to this one. So let's proceed. So I put x equal to 0, velocity equal to 0. I will put this velocity equal to 0 at 2 successive places. So let's see. We will say that if we do that, k1 will come out to be 0. Why? Because if we put 0 here and if we put x equal to 0 here, so it becomes cos 0. Cos 0 is 1, so it survives, but sin 0 is 0, so this one gets cancelled out. This is gone, and we have the expression after x equal to 0 and v is equal to 0 has been put in. 0 is equal to e to the power something into k1. That's all. So k1 becomes equal to 0 and k1 vanishes. So if k1 vanishes, let's see what we have here. We have this expression. It's interesting to see that the amplitude of vibration, this term, it's having an x dependent expression. That means the amplitude is dependent upon the distance from the transducer. In what way? As we move away from the transducer, x will increase, so will the amplitude. The amplitude goes on increasing as we move away from x, and this means that if you take the exponentially decaying horn, that means a horn whose cross sectional area is exponentially decaying, you will have this expression for displacement and velocity, and therefore the amplitude will definitely go on increasing as you go down the go down the length of the horn, and we have achieved what we started with, amplification of amplitude. Okay. Now what do we do with this part? We will say if we put once again v equal to 0, okay, if we put once again v equal to 0, let's put that and find out. So our first thing is achieved, amplification of amplitude is taking place. Next, let's see if I have to design such a horn. Okay, suppose someone says go and make a horn of exponential type. Okay, you make it, you know that it will amplify, but first question is how much length of the horn will you choose? So let's go for that. Now there is v equal to 0 whenever sine value is 0. Okay, so what we do is, let's see where sine value is taking. So it's basically a into sine something. So let's put the sine value 0, therefore we will definitely have v equal to 0. The amplitude cannot be 0. If amplitude is 0, everything is 0, everything is peaceful, we don't have to bother about that. So whenever in this particular expression the sine value becomes 0, let's have a look. Okay, so at x equal to L equal to lambda by 2, okay, at x equal to L equal to lambda by 2, as we discussed, at half the wavelength, once again we are going to have that particular condition. Let's see. So we understand that sine 0, sine pi, sine n pi, sine 2 pi, etc., etc., all these places the value of sine is going to be 0. So let this be equal to, we have already considered this to be 0. Now let this be equal to pi, the second case, okay, the second successive case. So if it is equal to pi, okay, then let's put it to be pi. Okay, this side you have pi, and in place of omega, where's omega? I've lost it. Oh, right, we have sent c to the other side, so it's c pi divided by omega x, and in place of x I have put length. Okay, length, whatever be the length, at this moment we are simply putting length. So put omega to the other side, it goes to the denominator, c goes to the numerator. So numerator c, denominator omega, denominator L replacing x, whole square, okay, because you are taking away this root over sign, and therefore you have 1 minus alpha square c square divided by twice omega, a 4 square omega square must be equal to this. That's good. That's good. So let's see what we get out of that. Now we bring in another particular variable. What's that variable? That variable simply is n. And what is n? N is the ratio of the final and initial cross sections of the horn, and it's equal to e to the power alpha L. Now what's that? If we take, let's quickly do that calculation here, e to the power, we know a is equal to a0 into e to the power minus alpha x, and in our case it is equal to, the final cross section is equal to e to the power minus alpha L, where L is the length of the horn. How much is it? I don't know. I have to find out in order to design it. Okay, so what do? We can say E by A0 is equal to e to the power minus alpha L, and therefore we can say A0 by L, A0 by A is equal to e to the power alpha L, which means if I take log, I will get ln A0 by A equal to alpha L. Okay, so here I am making a replacement. This is equal to ln of n. That's all. So I get ln of n is equal to alpha L. This is the thing that we have used. Why is this one used? This is quite a frequently used term. So we are introducing that terminology. Nothing else. No new idea. So looking at the previous expression, we'll have a quick look at that. This was our previous expression. So this is probably going to be intact, and we are going to simply replace alpha. Yeah, that's it. We had found out that n is equal to e to the power alpha L, and from that we had got ln n is equal to alpha L, and therefore we have alpha replaced by ln n divided by L. Okay, ln n, that means natural log of n divided by L, and therefore we have c pi whole square, etc., all the terms previously, and so therefore this is the expression that we get, and we start algebraically manipulating it. That means taking this term on that side, etc., etc. This we can recognize, this has been brought here to this side. 1 has remained on the other side, and c pi by omega L is here, so that we can easily recognize that c can be taken common, L can be taken common, omega can be taken common, and therefore it means that this will be depleted of hardly any of the terms. Pi can also be taken common and taken out, so that we have the final expression as this one. What's the change that has taken place from the other terms? Simply we have replaced omega by twice pi f. Okay, if we replace omega by twice pi f, what are we getting from the previous expression? Let's do it and finally put a seal to it. Yes, yeah. So we have, if you look at the expression, ln n into c divided by twice omega L whole square plus c pi by omega L whole square equal to 1. Now what can we do here? We can take L common here, and so that the other side will have L square. That's good. Equal to. So I am writing this side on this one. L square is equal to, c can be taken common, c is taken common, c square by omega square, and suppose I take pi square also common, and therefore I will have, this one is depleted of everything, so it has 1 plus ln n is still there holding the citadel, by pi whole square. Does that look correct? Let's see. C was gone, omega was gone, 2 is there still, 2. So what can we do about this? Let's replace omega square by 4 pi f square. So L will be equal to, in that case, C, pi will cancel, 4 pi square omega square, 4 pi square to f square, C by twice f, root over 1 plus ln by 2 pi whole square. Seems to be correct. Let's see. Yeah, exactly. We have got the expression that we had previously noticed. So this means that after all that calculus and all that analysis, we are ultimately coming to the conclusion that the length of the horn with exponentially decaying cross section can amplify the amplitude that we have seen, and its length should be this one. Its length should be this one. This is called half wave horn. That means its length is equal to half the wavelength. We can go for different lengths also. We need not necessarily stick to half the wavelength, but it's one of the most common ones. So let's take up a few numerical problems on this. There is a horn with circular cross section, and its cross sectional area is going down exponentially from the transducer end to the tool end. Find out the frequency below which this horn will not amplify. Oh, so it's a negative statement. The frequency below which this horn will not amplify. So basically it means that we will simply find out the frequency for which it will have negative roots, and for that we will say that okay, above this particular frequency it's going to have vibration, that means cyclic motion, and therefore below this frequency we are not going to have. So the variation in cross section is this one, and therefore we have previously seen, if you remember, this would have vibrational motion, that means cyclic motion, that means sinusoidal motion, only if this term is greater than 0. This was in the discriminant. So naturally, if you arrange the terms, ultimately it boils down to, if twice omega by c is greater than alpha, in that case you can have sinusoidal motion, vibration, cyclic motion, periodic motion. So just let's have a quick look at the previous case. This omega can be replaced by twice pi f, so that we will have 4 pi f. 4 pi f by c is greater than alpha. That's it. That 4 pi goes down and alpha climbs up, c climbs up, so that you have frequency is equal to or greater than alpha c by 4 pi. If you have this is the least frequency for which you are going to have periodic motion. Below this, any frequency will not amplify the amplitude, because simply it will not be periodic. And in fact, when we are designing, we generally make a check that the frequency that is being used, it's definitely at least 1.5 times this frequency, or maybe 2 times this frequency, like that. Okay. Let's take a numerical problem. There is a horn which is to work at 20 kilohertz, and its length is to be half the wavelength of the vibration. Okay, that's good. So the frequency is 20 kilohertz, and the length of the horn is half the wavelength of vibration. At the transducer end, the horn has a cross section of 8 centimeters by 8 centimeters, and from this cross section 2 of the sides, that means it's a square, so it has 4 sides, and from this particular cross section 2 of the sides are exponentially reducing to 4 millimeters. Okay, 4 millimeters. So it's reducing like this and becoming a knife edge sort of. It's moving like this and reducing this way. Okay, what does it read further? It reads that the other 2 sides remain at 8 centimeters only. If the velocity of sound in the medium is 4800 meters per second, find what should be the length of the horn. So we have to find out the length of the horn. So let's draw a quick picture how it looks like. That's it. The horn looks like this. The transducer is at the top, that I have not drawn, but the horn is it is gradually tapering off, and this side is 4 millimeters. Mind you, this edge is still 80. So once we are understanding, okay, this is the shape. Now comes the question of designing it such that we can find out its correct length, so that it's a half wave horn. So let's go on finding out the terms, I mean the dimensions that we have come across, like for example the natural logarithm of n, because as we know in the second expression that we have, this simply is the expression of the length of the horn. So see, A0 and A1, these are given to us. A0 is the original cross section at the transducer end, and this is the cross section at the tool end. So this is equal to the natural logarithm of n, and therefore we put in values. This is the area at the start, and this is the area at the end. 80 cancels, so basically it's ln 20. ln 20 is equal to 2.995732. Okay, so this has been found out. So this by 2 pi whole square plus 1, just let me see, into twice into c by 2f is equal to the length. Achha, what is the speed of sound in that particular medium of the horn? If the horn is made of steel, the sound will be traveling much faster than it travels in air, and it has been given. Let's have a quick check. 4800 meters per second is the velocity, and 20 kilohertz is the frequency. That's all. So we put 4.8 into 10 to the power 3 divided by twice f, 2 into 20 into 10 to the power 3. 10 to the power 3 cancels, and therefore after all these calculations we will have 133 millimeters. 133 millimeters. Okay, I will very much prefer that you carry out this calculation yourselves to cross check this one. There might be a simple careless mistake, so it will be good practice to follow the calculations by yourselves once, and if you find some discrepancy, please report it to me so that I can also correct it and then convey it to everyone. So the first part of the problem is done. 133 millimeters. Second, now we have to make a check. If you remember that expression, what was that? F is equal to alpha c by 4 pi. What does that mean? That means that we have designed it for 20 kilohertz. But what's the threshold frequency? That is a frequency value below which there will be no periodic motion, and we should generally be 1.5 to 2 times that particular frequency in order to have a safe region of, safe selection of frequency. So, alpha is equal to, we have already found it out, 2.995732 divided by the length, and that gives us 2.995732 divided by 0.133. This was the length. If you remember, we are expressing it in meters. So, this comes out to be 22.524. Okay, that's good. So, once we have this, therefore, twice omega by c is equal to, what is twice omega by c? Twice omega by c is this was the check that we were making. This was the check that we were making in order to be sure. I'll just go there. In order to make it sure that periodic motion is definitely going to take place, twice omega by c should be greater than alpha. So, twice omega by c is equal to 4 pi into 20 into 10 to the power 3 2 pi f. So, 2 into 2 pi f divided by c, 4.8 into 10 to the power 3 is equal to 52.359, and therefore, this particular term twice omega by c is much greater than alpha. Okay. We can look at it in another way. Let us find out the critical frequency. Okay. It is much easier to understand it in terms of critical frequency. That means a threshold frequency below which there will be no periodic motion, and for that we use the next expression. If you remember, f c was equal to alpha c by 4 pi. So, we put the values of alpha, we put the value of c, and we put the value of 4 pi here, and it comes out to be 8.6 kilohertz. So, are we at more than 8.6 kilohertz? Yes, we are working at 20 kilohertz. So, even if you double 8.6 kilohertz, we are even more than that. 20 kilohertz is more than double of that. So, we are in a safe zone of frequency. So, we have found out the length of the horn, and we have checked that we are working in a particular range of frequency which is in a safe range in comparison to the threshold frequency below which there will be no periodic motion. Acha. So, I have 1 or 2 minutes now left of this lecture. I would like to discuss one MCQ. This is actually connected with something that we will be discussing in more detail later on, but I am sure some of you will be able to understand what is the answer. In ultrasonic machining, surface roughness improves with increase in static load. Static load means the load which you are applying on top of the machine head in order to keep the tool and the workpiece pressed together. So, if you increase the load, the surface roughness improves. Roughness becomes less, surface finish improves, actually we should have said. So, one possibility is because hammering effect is more, and the grits get embedded into the workpiece surface due to higher load, and the damaged craters are all filled up, and therefore, surface finish improves. None of the others, and the grits get crushed at higher loads, create smaller sized damages, and hence roughness is less. So, the answer to this is the last one. Actually, grits get crushed at higher loads, and therefore, they are rendered into smaller grids, and these smaller grids give rise in turn to lower values of roughness, and surface finish improves. But you are going to lose in MRR. MRR is going to come down. So, with this we come to the end of the 7th lecture. In the next lecture, we will be dealing with the other parts of the ultrasonic machine. So, till then, thank you.